students, now let's start next lecture, lecture number 28 from topic second electronic spectra of transition metal complexes, and subtopic is electronic spectrum of hexaco titanium complex ion and spectrochemical series. Now let's first discuss electronic spectra of hexaco titanium complex ion. Now most important points include in electronic spectrum of hexaco titanium complex ion is as follows. Position of the band and number of peaks. In hexaco titanium complex ion, the metal ion is central metal ion is titanium having oxidation state +3, which has D1 configuration. D1 configuration means having only one electron in d orbital. Now there are 5 d orbital. All of you know that dxy, dyz, dxz, dx square minus y square and dz square. Within these 5 d orbitals, only one electron is present in case of hexaco titanium 3+. What is the atomic number of titanium? It is a 22. So when we remove 3 electron, only one electron is remain in the d orbital. Hence it is having D1 system or D1 configuration. The spectrum shows only one peak at 20,300 per centimeter, that is lambda value is 500 nanometer. Now only one peak because there is only one electron. Because of only one electron, transition is also 1. As there is only one transition, we get only one peak at this position. And the energy of that peak is 240 kilojoule per mole. Now this peak corresponding to excitation of one electron from lower T2G orbital to higher EG orbital. The excitation is from T2G to EG. As there is only one excitation, there is only one peak present at 20,300 per centimeter. Now second important point from this spectrum, intensity of the band. The band which is obtained, what is the intensity? The intensity of this spectral band is quite weak. It is a weaker one. The molar extension coefficient is 5 dm³ plus per mole per centimeter. The weak intensity of this band is due to the fact that the absorption corresponds to DD transition, which is forbidden by Laporte orbital selection rule. What is Laporte orbital rule? It is allowed only that transition which is having azimuthal quantum number change either by plus value 1 or either by -1. As it is a forbidden, that means there is a change is either 0 or more than ±1. So as it is a Laporte forbidden transition, so we get weak intensity. The transition takes place to some extent, still transition takes place to some extent. This is due to the relaxation by mechanism of vibronic coupling. In the previous lecture, we discussed about this vibronic coupling. Now third point is width of the band. So what is the width? It is observed that the spectral band is not sharp, it is quite wide or broad. This broadness of the band is because of overlapping of electronic transition and vibrational transition. So these are the three important points from the spectrum of hexaco titanium complex. Now fourth one is shoulder in the band. The peak of 10 at 20,300 per centimeter is not very sharp, but it shows a shoulder. This shoulder is because of it consists of actually two small peaks which are overlapping. That's why we get shoulder instead of sharp peak. This shoulder or bluntness is due to the some distortion in the molecule which is called as a Jahn-Taylor distortion, which takes place in the excited state of the complex molecule. So shoulder is because of one of the reason is as there are two small peaks which are get overlapping, and second one is due to the distortion which is called as a Jahn-Taylor distortion, which takes place in the excited state. These two reasons are responsible for shoulder in the band. So now this diagram indicate that this is the energy and this is frequency where we get this peak which is having blunt or shoulder at 500 nanometer value. So wavelength is 500. Frequency is 20,300 per centimeter. Now here this is 20,300 per centimeter. And color of this hexaco titanium 3 plus complex ion is purple. So there is a question in objective, what is the color of hexaco titanium complex? So answer is color of the titanium hexaco complex is purple. Now this diagram also gives idea about its spectrum. Now this is the T2G, lower energy level, having one electron get excited to Eg, where this is the excitation splitting of the orbital in hexaco-titanium complex. Now here this is the value 20,300 frequency value. Here we get blunt, not a sharp point. Now this diagram indicates a sign transition of Eg to Ag. This corresponds to the energy gap, which is a value is energy of 240 kilojoule per mole, 243, 240. Now this is the blunt, this is the peak of hexaco titanium 3 plus complex ion. So all these 4 points are important from the point of spectrum of hexaco titanium complex ion. Now next point is spectrochemical series. What is meant by spectrochemical series? When we study the spectra of a series of a complex of the same metal with different ligand. So here we get change for only ligands, not metal ion. It is observed that the position of absorption band get varies depending upon the ligand which are attached. So depending upon the nature of ligand, we get absorption band at a different position. Ligand which cause only a small degree of splitting, that is called as a that is called weak field ligand which cause small degree of crystal field splitting, whereas ligand which cause a large splitting are called as a strong field ligands. The common ligands which is arranged in the order of their increasing splitting power. So one is weak field ligand, second one is a strong field ligand. Between these, there are ligands which are in average. The order remains practically constant for different metals. This series is called as a spectrochemical series as it is based on spectral data and which is given below. Now this is called as a spectrochemical series. Now these are the metal ions which are having weak field nature, whereas these are the ligands which are having strong field nature. So in between this weak field and strong field, these are the ligands which are in average form. So this is called as a spectrochemical series where you can see that CO, that is carbonyl, is having highest crystal field splitting ability, whereas iodine, which is halogen, having lowest one. This series shows that the value of delta octahedral in the series also increases in the same order. So increases in the same order, that is from left to right. Thus ligand on the left side are weak field ligands. So these are the weak field ligands, while those on the right side, that is this one, are strong field ligands. The spectrochemical series, an experimentally determined series. It is difficult to explain the order as it involves effect of pi and sigma bonding. So sometimes this order may get disturbed. This is because of effect of sigma and pi bonding. So this is about spectrochemical series. The halides are arranged according to their electrostatic effects. Now fluorine, chlorine, bromine, iodine, these get arranged according to their electrostatic effect. In other cases, we must consider covalent bonding also to explain this order. The pattern of increasing sigma donation is also important. So now from that, halides are weak field ligands. Then after halide, oxygen containing ligands, then nitrogen containing ligands, and then lastly carbon containing ligands. So most powerful is ligand which contain carbon, then nitrogen containing ligand, then oxygen, and last one, that is weaker one, is the halides. The crystal field splitting produced by strong field Cl minus ligand, cyanide minus, is about double that of weak field ligand like halides. So splitting produced by strong field ligand